So let's address this AVL trees versus red black trees. So what happens with AVL trees is that the height is okay. Height of the tree is less than in red black trees. So if the height is less, so AVL trees have a smaller height, this implies that search is faster on average in AVL versus red black trees, right? So if the height is about 1.44 times log n, while here if let's say it's 2 times log n, then on average the amount of time you take is, okay, sure, it's a constant time, and computer science, at least theory, people don't care about constants, but if you implement, when you're implementing, you might care about these constants, right? The average time is 1.44 times log n, here maybe it's 2 times log n, and therefore you might prefer AVL trees over red black trees if your search, if your data structure is used most often for search. Okay, if you do, however, insert and delete are on average faster in red black trees. Okay, the reason is this. So red black trees are sloppy about maintaining the height difference. So on average they do less amount of rotations to maintain balance, while these guys, the AVL trees, have to do a lot of rotations so that it maintains the height difference of 1. So therefore the insertions and deletion times for red black trees are faster on average. Okay, so you see the trade-off here, right? So if your data structure is going to be used with large amount of churn, so things are coming in, going out, things are coming in, going out, very often, then you might want to use something like this, like red black tree, because you save on insert and delete time. However, if your insert delete times are rare, and most often your data structure is used for search, maybe you want AVL trees because you're paying a constant amount less in each search. Okay, so this is sort of one reason. So okay, so the other question was about skip lists, but I'll skip that because skip lists are sort of randomized, and now there are all these issues that all the issues that come with randomized algorithms. So essentially are the drawbacks of skip list. That there is no deterministic time on any of the operations. We can only guarantee in expectations or with high probability. Okay. Sorry. Oh, skip list. So skip list, you could say insert takes log n time with high probability. Okay. You might be happy with with a statement like that. So the probability that insert takes more than much more than log n times is exponentially small, but maybe you're not happy with that. Maybe you want a deterministic bound. It says I want only c times log n. You're still allowing some small probability that insert will take a very long time. It's not ruled out, and you may not be happy with it, especially if you're interested in, let's say, real-time systems. You're building a real-time system where you really want the system to you want the insert and delete to take some fixed amount of time and return back. Then you want to ensure that you may not want to take this chance. So this is sort of the arguments for and against AVL versus red black trees or 2-4 trees and so on. Okay. So the other question was about books. So one nice book, of course, is whose name I forget. I think this is called. I think the title is Algorithms and Data Structures. It's called the basic blue box. So I like this book because it's small. You can carry it around, unlike CLRS. So that's one big advantage. The second advantage is that it does talk a lot about the implementation issues of data structures and algorithms, especially implementation in C++, in Java, implementation for large data sets. Right? What happens if the data becomes very large? So let's say you want to implement a binary search tree, but now the number of elements is too huge. What are the issues you face? So these are addressed, which I don't see addressed in any of the other books. The other, okay, so that's the other advantage. And the other thing is that they focus on what is called certifying algorithms. Okay. So what are certifying algorithms? So they are the following. Okay, so I'm digressing a little bit, but I hope that it's time well wasted. So suppose there's an algorithm. Let's say you see an algorithm, you've proved it correct, very good. Now you go and implement it, and you know that if you implement it, invariably there are bugs. Some that you spot, some that you don't, but there are bugs. Right? The algorithm is correct, but the implementation is incorrect because we are all poor programmers, right? Okay. Some of these bugs you can catch, but many of these bugs you may not catch. But now suppose I want to give you this piece of code and say, okay, now you go ahead and use it. I am convinced it works. You shouldn't trust me, right? So okay, fine, I don't have time, so I'm going to use your library. I'm going to use your program, which is an implementation of a correct algorithm. But I don't trust you as a programmer. Your programming abilities are suspect. Okay, although you've checked it and so on. So I still use your program and generate output. What would I like to do? One thing I could do is do a formal verification. Right? I mean, verify the correctness of this program, but for formal verification, it just doesn't scale. You can't do it for large programs. Okay. So what is the other thing? I could do an instance optimal per instance certification, which means I give you the input, and your program returns an output, and I can write a small program which is much simpler than the original program, which will check and promise me that the algorithm is correct, that the output is correct. For example, let's say you implement a sorting algorithm. You claim that your algorithm is a correct sorting algorithm, it's correct implementation of a sorting algorithm. We know many correct sorting algorithms, but maybe somewhere there is a bug. So I don't trust your program. I'm going to write sort. I'm going to call your sorting algorithm. I'm going to take the output, but I can check in linear time if it's sorted, if your output is sorted. So I can scan through and check your output is sorted. Now you will agree with me that just checking if the output is sorted is easier than actually implementing a sorting algorithm. So I can write this certification. I can say that, look, I'm convinced. I don't want to formally verify, but I'm convinced that this is this instance, at least on this input, you have not messed up, and I can take this output and be happy with it and run with it. Okay. So the other perspective, which is different in some of in this compared to the others, is sort of the focus on certifying algorithms, right? And this is I mean, I've tried to do it a little bit in my algorithms classes, but not sufficiently. But I think this is a very nice nice notion. For some problems, there are easy certifying algorithms. For some problems, it's not so straightforward what a certifying algorithm would be. Okay, so we can get on with the truth. Okay. So any questions? Okay, so let's look at another data structure, which is called union find. So I have till 1, right? Okay, so what is union find data structure? So this is a data structure that where we want to maintain So we want to maintain a collection of sets. So I have a universe of elements, right? So I have a universe of elements and I want to maintain them in some sets, disjoint sets. Okay, so this is set 1, here is set 2, set 3, and so on. And there are these disjoint sets and each has some elements. Okay, so I want to maintain these disjoint sets. So what are the queries I want? So if I give you an element x, given element x, which set does x belong? To which set does x belong? So we want to be able to answer this question. So I give you an element x. If I give you x, then your output to this query should be, well, x belongs to set S1. Okay, so this is called the find operation, which is the find in union find. I want to find this element x, which is tell me which set does x belong to. Okay, so this is one. The other operation I want to support is union, okay, which can take two parameters, x and y, which are both elements of my ground set. Okay. So these are elements of the ground set x, and what does the union operation do? Create a new set that is the union of the set of x and the set of y. So the set containing x, and this is the set containing y. Okay, so we want to, so for example, if x is in S1 and y is in S2, if I call union of x comma y, the set, so what we do is we create a new set S1 2, that is the union of 1 and 2. Okay, so what we would like to do is we want a data structure that will, if you give an element, will tell you which set it belongs to, or it will allow you to create a union of two sets, right? So union will essentially find the set that x belongs to, find the set that y belongs to, and then create a union of x of these two sets, right? So what we want to maintain is this collection. Okay, so is this clear? Okay. So why do we want to maintain something like this? Is fairly natural, but it's sort of one key application of union find is in implementation of minimum spanning trees. So you're given a graph undirected, connected, and let's say a weight function from the edges to the natural numbers, and this is the input to the MST problem, and what we want is to compute a tree T spanning V, minimizing sum over E in T, weight of E. So we want to compute a tree whose sum of weights of the edges is as small as possible, that spans all the vertices in the graph. Right? So for example, if you had so you might pick this tree. This is a spanning tree because it spans all the nodes and whose weight is 1 plus 1 plus 2, which is 4, or you might pick which is also a spanning tree but whose weight is larger, right? So 4, 6 and the weight is 7. Okay, so for this graph possibly this is the minimum spanning tree. Okay, so we want to compute a minimum spanning tree. So there are two classic algorithms that we all know, which is Prim's algorithm and Kruskal's algorithm. So let me quickly tell you Kruskal's algorithm works as follows. So we want to so we sort edges in non-decreasing weight order. So let's say weight of V1, weight of V2, okay, start with T to be the empty set. Recycling. Okay, so this is Kruskal's algorithm. So what you want to do is to sort the edges in increasing or non-decreasing order of weights, right? And we scan these edges in this order, starting with an empty tree. And at each step, you look at this edge, you try to add it. If the set of edges T union EI is acyclic, let it add the edge. If it creates a cycle, then don't add the edge and move to the next one. This is the algorithm. So, so for example here, so let's say we break ties arbitrarily. This is the first edge and this is the second edge. Right, so we would look at this edge first, then ordering would, let's say E1, E2, E3, E4, and we would add E1, which is fine. Let me make it more interesting. So I add one more edge and this would become E4, this guy would become E5. Right? So now you add E1, which is fine. So the tree is acyclic. Then we add E2, the tree remains acyclic. Now you add E3, oh sorry, okay. So you add E3, the tree remains acyclic. Now when you add E4, you create a cycle, So we don't add E4. And of course, you don't add E5 because you don't need it. Okay. So this is Kruskal's algorithm. So what we want to do, so what do we want to do at each step? When you add an edge, you want to check if it creates a cycle, right? So at any intermediate stage, how does the set of edges in T look? So how does T look at any intermediate stage? The set of edges in T. So set of edges in T forms a graph, but it's a graph with some special properties. It's a tree. So let's look at this picture. Let's look at the graph. Maybe say 1, 2, 4. I'm going to add one more edge. Let's say this guy also has a weight of 1. So why not make this 3? And this maybe 2. Okay, so now let's label them. What are the labels? This is E1, let's say, E2, E3, E4, E5, E6. Now let's run Kruskal. Initially this is the tree, it's empty, there are no edges. Then we add E1, we're processing them in this order, and then we add E2, the tree is acyclic, whatever, set of edges, the graph in the subgraph of the set of edges is acyclic. I mean the other vertices are still alive, so they're sort of sitting there. So maybe I should have said that initially the tree looks like this. A set of nodes with no edges. Okay. So then we look at E1, we try to add E1 and we're fine. So it doesn't create a cycle. Then we add E2, doesn't create a cycle. Then we add E3, doesn't create a cycle. So this doesn't create a cycle but is connected. This doesn't create a cycle but is connected, but these two are not connected. So this? So this is how the picture looks. No. So we have not completed the algorithm. We have not completed the algorithm. But at some intermediate stage, this is how the set of edges, the graph induced by the edges in T, it looks like this. So in general, if you look at the graph at some intermediate stage, if you look at the graph induced by the set of edges in T, what is the property the graph has? It's a forest. Yes. So it's a forest, right? So a forest at some intermediate stage is a forest, right? So what we have as a generic picture of Kruskal's algorithm is the following. There is some tree T1, there is some tree T2, there is a T3, and so on. Right. So at some intermediate stage of Kruskal's algorithm is this forest, this collection of trees. Okay. Now we want to process this edge E sub I. This is the edge we want to process now. And what do we want to know? We want to answer the following question: is T union E sub I acyclic? Which means if I add this edge E sub I, does it create a cycle, or is the graph still acyclic? Okay. So how do we check this?
If this is a part of a single tree, then it will be cyclic. It will add a cycle.
Yes.
Both the vertices are the same tree.
Yeah. So let's say the endpoints of EI, U and V. So okay, so this is U and this is V. If U and V lived in the same tree, then surely adding the edge UV, so there is a path from U to V in the tree. Now you add the edge UV, you ended up creating a cycle. So if U and V live in the same tree, they form a cycle. But if U lived here and let's say V lived in another tree, disjoint from U, there is no path from U to V. Now if you add the edge UV, it's clear, and we don't form a cycle. The graph remains acyclic. And now what is the forest? The forest consists of all of these trees, T3, T4 and so on, but we have a new tree which is T1 union T2. Right? We've created a new tree by connecting these two forests by an edge. So one question is, how do you implement this? Now this looks uncannily familiar with what we started with, the union find data structure, right? So what do we want to know? Given an edge UV, given an E sub I whose endpoints are U and V, we want to know which tree does U belong to. And then you might say, well, U belongs to T1. Then you might ask, which tree does V belong to? And V belongs to, let's say, T2. And if T1 and the answers are different for these two endpoints, then we know that they live in different trees and we can add an edge. And now you add an edge, you create a union of these two trees. The new tree, the set of nodes in the new tree is the union of the nodes in these two trees. So you've created a union. So this is precisely what we started with. Right? We wanted a data structure that for each node, for each element can find the set it belongs to, and we create union of these sets. It's exactly what we wanted. This is exactly what we want, and this is exactly what the union find data structure is. Okay. So before going to what is the obvious way to, so let's ask the following question: what is the naive way of implementing this if we don't have access to the union find data structure? So how would you implement this if you did not know the union find data structure, and how long would it take? Using? Fine, I mean you could use sets, but you see what you want to do. Okay, so I just wanted to show you the connection between union find data structure and say that what the union find data structure claims to provide is precisely what you want when you implement Kruskal's algorithm. But now I'm asking, let's forget that we know about the union find data structure. If you did not have access to the union find data structure, then how would you go about implementing this? What you want to do is you want to check if T union EI, E sub I is acyclic. This is what you want. And I'm asking you, how would you go about implementing this?
We should be finding out whether there is a cycle which is getting formed by which.
Yes, that's exactly what you want to do. How would you detect if there is? You can maintain an array. Also, which elements? Okay.
We have a very naive approach to that. All
Okay.
the elements in the array, we could assign a representative for each element of the array, and initially all of them would be their own representative. Whenever you create a union, you choose one of the element as the representative, and in that column.
Okay, so you are already walking, but you're already going down that direction. So suppose you did not have access to disjoint sets. So what is the naive way of implementing this? That's what I'm asking. So sure, I mean this is what we'll eventually come down to. We'll have these representatives and we'll do all kinds of things. Okay, so you have these n elements. So initially all the nodes live in their own array.
It's a two-column array.
Fine. So you have this array of singletons, and there are n arrays, each for an element. Now you add an edge, UV, let's say E1, which is, okay. So let's say this is between, let's say 1 and let's say 4. So what do? You want to create a new array. Is that what you said? No.
Choosing the 1 or 4 as a representative and update that representative information in the.
Oh, I see. So each cell contains a representative information.
So there are two information in each cell. One is the value of the element, other is the value of its representative. So it's a 2-column array.
Fine. Okay. So I could just say that initially. So let's say the cells are numbered 1 to n. So we don't care about that. So now all you're going to say is, well, maybe each element in the array we store its representative. So for each, initially they are their own representative, right? And now if you look at the edge UV, then you want to say that, well, maybe 4 is the representative. Maybe by convention you want to say maybe the larger numbered guy is a representative, and so maybe the point like this, and so 4 is the representative. Fine. So now I give you another edge, E2. Now I want to know, does it create a cycle? So you've added the edge E1, which is, let's say 1, 4. Okay. So you added 1, 4. This is E1. Right. Now you've got this new edge E2 that is arrived. We want to know if it creates a cycle. Well, certainly E2 cannot create a cycle, so we can just go ahead and do it. So maybe it's from 2 to okay, so maybe 2 to 4. Okay, so maybe E2 is the edge to 4. Okay, so maybe this is E2. Right, now E3 arrives.
Now you give the information into the so
Yeah.
all the representatives are now 4, 1, 2 and 4.
Okay, so this guy points to 4, this guy points to 4, and 4 points to itself. Okay, now E2 arrives. Okay, now, okay, so let's say E3 arrives, which is 1, 2. Now what are you going to check? You're going to check 1, look at its representative, which is 4. For 2, the representative, which is 4, and you discover that the representative is the same, and therefore they are in the same set, and therefore we don't add it. They would create a cycle. Okay, fair enough. Okay. Okay, so let's just go with the union point research. So let's see. So now let me ask you the following question. Let's say this is how we implement it. We are going to also use the convention that the representative is the element with the larger index. Let's say. Okay. So if two elements belong to different sets, we are going to say the one with the larger index is representative. So then, what is the time complexity of this operation? How long does it take to check if T union E sub I is acyclic? Yeah, so I mean, this is precisely what we are doing. We are maintaining. So you are maintaining an array indexed by the nodes, and for each node you maintain the information of the and one of the nodes is going to be chosen as the representative of that set. If the node is chosen as the representative of that set, the name of that set is a representative. Right. So initially each guy is his own representative from 1 to n. Right. So initially we start with an array 1, 2, 3, blah 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 up to n for the nodes numbered 1 to n. So the set that a node belongs to is itself. So each one is a singleton. When an edge arrives, we are going to pick one of the nodes, one of the endpoints. Let's say E1 is the edge 1, 4, and let's just use some convention that the larger label node is the representative. Then if the edge E1 arrives, I'm going to just replace this by 4, and therefore we know that 1 and 4 belong to the same set. Right? We know that 1 and 4 belong to the same set, and the set is called 4. Just 4 is the representative, or the set is called 4. Right? So if I want to know what set does 1 belong to, it belongs to the set to which 4 belongs. And now if we added the edge E2 like this, now 2 would go, it would replace the representative of 2 as well as 4. And now you ask, what set does 2 belong to? Well, 2 belongs to the same set as 4. 1 belongs to the same set as 4, 2 belongs to the same set as 4, therefore they belong to the same set. And 4 belongs to the set called 4. Okay, we can represent this pictorially. I mean, instead of thinking of an array, we can represent it pictorially as, in starting with a set of nodes 1, 2 up to n, each pointing to its representative. You can use an arrow and say each one points to its representative. So when the edge E1 arrives, what we've done is removed this edge and made 1 point to 4. When E2 arrived, we removed this edge and made this guy also point to 4. Right, so what we get is really a forest. Right? So this is okay. So this is exactly the implementation we want. Well, is T union EI acyclic? Well, look at the set that one belongs that one endpoint belongs to. Look at the set that the other endpoint belongs to. Do they belong to the same set? If they do, they belong to the same tree in the forest. Therefore, they will cause a cycle. So we won't add it. If they belong to different sets, they belong to different trees in the forest. You can bravely go ahead and add it. But then what? Okay, so let's say E1 arrived, E2 arrived, E2 is the edge 2, 4. So in our graph, at this point our graph looks like this. E1, E2. Yeah. So now maybe something else happened, E3 arrived, E4 arrived, and now the picture looks like this. Okay. So let's give these, maybe these are node number, let's say 5, 6, and 7. Okay, these are nodes. So what has happened so far is E1, E2, E3, and E4 have arrived, and what we've got is this picture. Now E5 shows up between 4 and 7. What will you do? You would check which set does 4 belongs to. 4 belongs to the set to which 4 itself is the representative, like so. Right? And you would check that seven belongs to the set for which it is the representative. So they belong to different sets, so we can add the edge in the graph. So if you add the edge 4 to 7, we add the edge E5, then how should this picture change? Do we need to do that? We update the representative for one of them, right? So let's say we 4 will point to 7. Do you want to change 1 and 2, or does 1 and 2 have to two things, you could do two things. One is that you could change the pointer of 1 to 7 and 2 to 7 and so on, or you could say, well, 1 points to 4 and 4 points to 7 and 7 points to itself. Anybody who points to himself or herself is a representative, and therefore we could follow these pointers up and sort of discover now that if you get a new edge 1 5, then you know that, well, they belong to the same set, because I will follow these pointers up to 7 who points to himself, and I would follow these, so 5 would follow these pointers up to 7, and so we know that 1 and 5 belong to the same set, right? So there are two options: either you can make all of them point to this one representative, or you could sort of form this forestry thing that so these guys can, now you can just follow these links and go up to the first to the node that points to itself as a representative. Okay. Now my question is, so the only thing we've done is we have only said that, look, who is the representative? The guy with the higher label, and that's just a convention. Okay. Now the question is, how long does this take? So what is the complexity of this operation if we maintain this data structure? In the worst case, what is the complexity of this operation?
Such links are maintained.
Sorry?
If such links are maintained.
So this is the data structure we have agreed to maintain. Now we want to check if T union EI is acyclic. So we want to look at the endpoints of EI. Now you see, so we are not pointing. So we are going to maintain this forest-like structure. So 1 points to 4, 4 points to 7. Tomorrow if something else comes, then 7 might point to something else. Sorry?
Are we changing the links of 1 and 2?
No, we are not changing the links of 1 and 2. We are only changing the root for now.
Size of the set would be the
Yeah. So
number of comparison, means number of links to be traversed in the workspace.
yes. So how bad could it be? Right, that's right. So in the worst case, so what do we need to do? We want to use, so this is a union find data structure, okay, approximately. With a little more work, it is going to be the union find data structure with which will work efficiently. But essentially this is what it is, right? It's just a forest, a directed forest with all the nodes pointing up to the root, and the root is the representative. Now what could happen? So my question is, what is the worst case for find, which is what you want to do. When you get an edge, you want to look at the endpoint and you want to find its representative. You want to follow up the links and find its representative. So the question is, how long does find take, right? So how long does find take? In the worst case, find can take linear time, right? So can you give me an example where find can take linear time? Fine. No. You'll have to do unions. You have to do a couple of unions so that even. No. So you're going. So you're maintaining this data structure, right? So what are you doing?
Then 2 is added, then 3 is added. So every time the point will point to the larger.
So let's look at this picture. So this is exactly 1, 2, blah blah blah, up to n, right? So it might be that you now, let's say, you want to take a union of these two sets, and you make 1 point to 2. Okay, so now your picture looks like this. There's 1, 2, and the other guys are living all by themselves. Now 3 comes, and you make 2 point to 3 and say, okay, now we'll choose 3 as a representative. 3 is our exactly. So now 3 is our leader. Then when 4 arrives, we make 4 our leader. Then 5 arrives. Each new person who comes becomes the leader or the representative. And now if you want to find what set does 1 belong to. You have to walk along this long path of length roughly, and so it could be that your find takes linear time. You see, in the graph we have no control over the order in which things come. The only convention we have maintained is that we are going to, our convention was the guy with the larger label is the guy who is going to be the representative, which is why we ended up with this sort of sequence. So now if you say find the endpoint of u of this one endpoint of u of this edge, you might have to walk up a linear number of steps. So therefore, to check if it's acyclic, you will have to do 2 find operations for each endpoint. That both take linear time, so this operation can take linear time. If this operation takes linear time and we run the loop m times, what is the running time? We are doing this for each edge, right? For each edge, we are doing 2 find operations.
Why don't we store the information about the representative at every node itself? Suppose I am for every element along the node.
That's what you're doing. But you see, okay, good. So this is the second idea that we had, which is that when you make, let's say, when 3 arrives, let's say, so initially the picture was this. We made 2 the representative, and so our picture looked like this. When 3 arrived, well, you said, well, let's make 3 the representative, and the idea was to update the representative for 1, which is to go back and make this guy also point to 3. This was the second idea that you had. Okay. So now, how long does union take? Right? If you want to do a union of 2 things, right? You have to do the union of these two forests. You will have to if the root pointed to this guy, then you are saying, well, let's go inside and change the pointers of all of these nodes inside to point to this root. Well, now your union takes a long time. So if the edges, if they actually belong to 2 different sets, the 2 endpoints belong to different sets, you have to create a union, and now your union is going to take a long time. Your union will take linear time, and you run up with a quadratic time algorithm for Kurzka. So the naive implementation, even with this data structure, is a quadratic time implementation of Kurzka. It takes quadratic time. So you want to do something cleverer to get this running time down. And what the cleverness is really a natural thing. In the union find data structure, I showed you what the problem is. The one problem is, well, just making somebody point to somebody else with a higher number is not good enough. You might get these long chains. Making everybody, if we take a union, making everybody in one tree point to the next one has a problem, because now your union takes a long time. So we know these 2 problems. The fix for these 2 problems is natural, is sort of very simple and naive, and this is what any programmer will do. The entire complication of union find data structure is not in the operation you would do, but in the analysis. And what is amazing is something so natural and simple that you might naturally think of leads to such sophisticated analysis, and all this complication is hidden underneath something so simple. So how could you speed it up? So let's look at the first way, wherein we did not make union expensive, which means we did not make all of these guys point to this root. We just made the root of one forest point to the root of the next, right? So this is this guy, and we made this root, let's say, point to this one. Okay? It's not a linked list. No, because there are multiple pointers. It's a forest. It's a directed forest. It's not a linked list.
I'm saying it's as good as going with
the way we have now currently implemented it. It can degenerate into a linked list. Similarly, exactly like the binary search tree, if you don't do anything, it can degenerate into a linked list if you just add numbers in increasing order. The same sort of situation is happening here, in the sense that if you're not careful, you might end up with something like a linked list, which is a bad implementation. So fine. So let's look at the first condition. So we just made the root of one forest point to the root of the next. So if you want to find the representative of x, you're going to follow these links up to its root, then jump up here and say, okay, v is the representative for x. The problem with this is that you end up with this long chain. So how should we avoid these long chains? How should we avoid these long chains? Let me make it more dramatic. Yeah. So they say this is one forest. Okay. So let's draw this picture. So this is one forest. Okay. So these are all pointing towards the root, and this is the other one. And they're all pointing up towards the root.
So the root of the larger one should be made the representative.
The root of the larger one should be made the representative, because if we do that, then for all of these guys, when you want to find, you're going to take this long path and point to this, right? But if you do that, then only so these guys remain the same. These guys, their height is smaller. All of these guys have to travel a shorter depth to the root, and so it sort of balances out the height. Right? This is the natural thing to do, and indeed, it's called union by rank. So what do? We store for every node its rank. For every node in the forest, we maintain a rank. Right? So now the root of this forest has a rank, and the root of this forest has a rank. Well, instead of making the lower labeled one point to the higher labeled one, we make the one with the lower rank point to the guy with the higher rank. This makes sense, right? I mean, it sort of is not. So, but first I have to define formally what is a rank and what is rank and these things. But this is sort of the anybody would think of it, right? I mean, this is sort of the most natural thing to do to decrease the time taken for find and to avoid this linked list kind of thing. Okay. Okay, so how do we define rank? Or how should we define rank?